In the last lecture, we talked about something called permutations. Right? A permutation is an ordered arrangement of the elements of a set. Well, the obvious next question to ask is, if we can count the number of ordered arrangements, well, how about the number of unordered arrangements? And I've got two examples here that illustrate the difference. In both cases, we have a group of 4 people, and we want to select 3 people from that group. Right now, in the first scenario, once I pull those people out, I'm assigning them to specific roles. One of them is going to get to be the chairman, the other is going to get to be the vice chairman, and the other is going to get to be the secretary. And the other one, I'm not doing that. All I need to do is grab these 3 people, and they're both going to be, in a sense, equal members of this committee. The first scenario is a case where the order makes a difference, right? Because you think when you're doing these little lines here, like we did when we were using the multiplication rule, I'm labeling these. This one is the chairman, this one is the vice chairman, and this one is the secretary. So if I do Alice and then Bob and then Charlie, right? Alice, Bob, and Charlie, that's a different arrangement from Bob, then Charlie, then Alice. So in this case, the order I pull these people out and assign them to these positions makes a difference. In scenario 2, as I said a minute ago, right, there is no ordering here. I'm just picking all of these people, and they all get to be equal members of the committee, no special responsibilities, no special votes, or nothing. So in scenario 2, if I choose Alice, Bob, and then Charlie, versus Bob, then Charlie, then Alice, there is no difference between these two. Everybody ends up having the same rights, the same responsibilities, so forth. Right? So this scenario 1 here would be an example of the permutations that we talked about in the last lecture. The scenario 2, this is the new thing that we're going to talk about here in this one. So our discussion here of unordered arrangements is going to borrow some from the set terminology that we talked about in an earlier series of lectures. When we're talking about a collection of objects, for example, the collection that we're going to be making these selections from, well, a collection of objects is a set. And since we're going to be picking an unordered selection from that set, right, what we're looking at here is going to be a subset of the original set. And the unordered part is really important here, right? Because remember when we were talking about sets several chapters back, sets are all unordered collections. Right? So it kind of makes sense to borrow some of that set theory terminology here. So what we're starting off with here is these two numbers, n and r. N is the size of the original set. Right? So we're starting with a set of n elements, and an R combination is a subset of that set that has R elements. And so what you see now let's jump back to the first sentence. The first sentence is let n and r be non-negative integers with r less than or equal to n. Okay, hopefully you see why, right? We can't select more elements out of that set than it actually has, right? So we have to put that little caveat in there that r has to be no bigger than n. Okay, and the way we write this, right, the number of R combinations, which is what we're really going to be looking for here, we write that C n comma R or NC R. Well, sometimes I'll read that N choose R. And you notice this parallels the notation that we used for permutations. We're talking about permutations, it was P n comma R or N P R. So very similar notation. We're just changing the P for permutation to a C for combination. And there is one other way you'll sometimes see that written, and that's with this kind of column-like structure here. All right, so those are our names. Right, we've got the definition. We've got some notation. What we want to do next is think about how can we actually calculate this? How can we actually calculate the number of subsets of a given set with a given size. So our goal here is to find a formula that lets us calculate the number of R combinations from a set with n elements. Right? And to do that, we're going to follow a process very similar to what we did with permutations. I've got a specific example here. Right? And I want to walk through kind of figuring this out for this specific example, and then we'll see if we can't replace some of the numbers with variables and generalize this to the kind of general formula that we're really looking for. So the question here is, how many ways can 3 people be chosen from a group of 4 people to be members of a committee? Scenario 2 from the previous slide. So what I want you to do here is I want you to kind of see if you can't think through this a little bit yourself. All right, in the first column here, I want to put all of these combinations. I'm kind of giving you a hint. There's going to be 4 of them. All right, so for example, I'm going to use, we're talking about a group of 4 people. It's a very common approach here. I'm going to call these people A, B, C, and D. Right, so one of my combinations here would be A, B, and C. Right now, at this point, I don't want to put BAC as one of my combinations because that duplicates the elements in this one. Remember, the order doesn't matter. All that matters is if it has the same 3 letters, I'm not going to add it again. So I'm not going to put BCA. I'm not going to put CAB. I'm not going to put anything else that has just those 3. All right, so why don't you go ahead, if you like, pause the presentation here and see if you can't work that out. See if you can work out what the 4 of those are. Then jump ahead to the next slide. Okay, so here are my 4 combinations of this group of 4 people. Right now, the next step in the remaining columns here, I want to write out all of the possible permutations of these 3. So for example, here I would put ABC. Then another permutation of that is ACB. Then another one is BAC, and so on. See if you can't do that for all 3 of these rows. Write out all of the permutations of each one. Yes, I'm giving you a hint again. There are going to be 6 of these for each row, but you knew that already, right? What we're doing here is you're listing all of the permutations of each set, and our permutation formula told us, because this set, we're doing 3 permutations of a set of 3 elements, so we expect from the permutation formula that this will be 3 factorial, which is 6. All right, so go ahead and see if you can write all of those out. So I don't want to make you sit and watch me write all of these lists out because it gets a little tedious. So I just went ahead and put them all in here. You may have things in the individual rows arranged a little differently. You might have some of these values flipped here, for example, and that's okay. Right? All that matters is that you didn't miss one and that we have the right count, because that's really what we're focusing on here. Okay, so how can we figure this out? Well, first, remember what we're looking for. Right? We're looking for a formula for calculating the number of 3 combinations from a set of 4 elements. So we're looking for a formula for calculating 4C3. And that's the number of rows we have in our table. Okay, so what I want you to kind of flash back to like elementary school multiplication. And you learned pretty early on that you can find the number of cells in a grid like this by multiplying the number of rows by the number of columns. Okay, so the number of cells equals number of rows times number of columns. Okay, the number of the number of rows is 4 choose 3. That's the number that we're actually trying to find. The number of cells, how big is this entire grid here? Well, if you look at those things, what we ended up with is a list of all of the 3 permutations of a set of 4 elements. right? So the number of cells is 4p3. Okay, and how many columns do we have? What do we do in each column? In each column, I took a set with 3 elements and wrote out all of the ordered arrangements of those 3 elements. Right, so the size of each row here, the number of columns, right, the width of each row is 3p3. Right, you can confirm pretty quickly, go to the formula, right, 3p3 is 6, and that's how many columns we're seeing. All right, so this tells me what I need. Right now I can solve for the combinations. 4c3 is equal to 4p3 divided by 3p3. And if you go to the formula, right, you put numbers into the permutation formula, you should see that is 24 divided by 6, which is 4. Okay, so before we go a step further and try to generalize this, try to get n and r in there instead of 4 and 3, what I want you to notice is for every combination, there were 6 permutations. So in a sense, the permutation formula is overstating the number of combinations by a factor of 6. Right? So when we factored out, let me write this here. This is 24 divided by 6. When we factored out these extra 6, we got down to the actual result that we needed. All right, so let's see if we can generalize this now. All right, so I'm going to start from the same base. Number of cells equals number of rows times number of columns. And now instead of doing 4 and 3, we're going to do n and r. Right, so I'm going to assume we have a set with n elements, and we want to count the r combinations. All right, well, those are combinations. Those will be the number of rows again. Right, so the number of rows is going to be n choose r. That's the thing we're trying to find. How many cells are there? Well, again, those are the total number of r permutations of a set of n elements. So this is going to be np r. And how many columns do we have? Right. Well, each of these individual combinations here has r elements in it because those are the size of the subsets that we're looking at. And I'm going to take all of the possible arrangements of them, all the possible permutations of them, and put them in the columns. So that's going to be r, excuse me, that's supposed to be an r. That's going to be r, p, r, number of permutations of r elements taken from a set of r elements. And now I can get my formula. Divide by rpr, and we get ncr is npr divided by rpr. That's fine. That's a perfectly good formula. You could actually use that. It's not usually how this is written. All right, usually the way this is written is we're going to take this a step further and we're going to put the individual formulas in here. Right? NPR is n factorial divided by n minus r factorial. And RPR is r factorial divided by r minus r factorial. Okay, r minus r factorial, that's 0. Excuse me, r minus r is 0. 0 factorial is 1. So that denominator is just r factorial. Okay, so this is, I'm sorry, I know I'm zipping around here because I'm running out of room. This is n factorial over n minus r factorial over r factorial. And if we clean up the fraction, this is n factorial over r factorial times n minus r factorial. And that's it. That's our formula. All right, that's our formula for the number of r combinations taken from a set of n elements. So this slide just summarizes those results using all of our new notations. These three expressions on the left here, those are just three different ways. I don't know why we need three, but there are three ways that are commonly used. Those are the three different ways for writing the number of R combinations from a set of n elements. And on the left, on the far right here, that's the formula that we just derived. Right? That's the formula that we're going to be using. Okay, so at this point in this lecture and the last one, they've both been very theoretical. We spend a lot of time going over definitions and deriving these two formulas. In the next lecture, we're going to look at a bunch of specific examples, see how we can use these formulas to actually count specific outcomes.